Okay. Hello, everybody, and welcome to this AJS. Today, I'm really happy to have with us Giulia Sambataro, and she will talk about a nonlinear reduced basis approximation of discrete contact problems in crowd motion. So please, Giulia, the floor is yours.
Thank you. Thank you to all the organizers for this kind invitation. And yeah, I'm very glad to be here talking to you about my current research project that I'm conducting in Cermix lab at Ecole des Ponts in Paris and in collaboration with Virginie Larcher. And as you said, we are working on nonlinear methods for contact problems. I'm starting with the description of the problem we are interested in, and that's a category of problems that are discrete contact problems for crowd motion in presence of obstacles, and similar models also describe the flow of granular materials. And you may be interested in different things, for example, in estimation of evacuation time, for example, in case of emergency, of also predict areas of high crowd density and also estimate contact forces. There are several models describing this phenomenon. There are microscopic models that are more stochastic models. What I'm working in is a microscopic model which is proposed by Maury and Venel. I cited here the reference, and now I'm describing this model that I adopted. We have a particle system of big NA agents, which are identified as rigid disks with centers Qi that is in R2, since I place myself in a two-dimensional setting. And I wrote here and count the possible total number of contacts among agents. You should, of course, add also the possible contacts with obstacles. And this model is proposed for very congested situations. So to avoid collision that you cannot avoid, in principle cannot avoid, positions have to belong to a feasible configuration set, curly Q, that is written in terms of assigned distance among agents. And this distance has to be non-negative. We can also express the same constraints in terms of velocity, that is the following. When agents touch each other, we have a contact, and so they have to move away to separate. This set CQ is a closed convex cone, and also we remark that it is not continuously dependent on Q, on the positions, and that makes the problem more difficult. This problem, that is dubbed DCP, discrete contact problem, is formulated as an optimization statement with constraints, in which we seek the velocity as the Euclidean projection of some spontaneous velocities onto a feasibility set for velocities with a certain initial conditions for positions. The spontaneous velocities are the velocities the agent would have without taking care of other agents. And here is an example. For example, velocities in this region could be written in terms of a certain constant S, and the gradient of D that here express the geodesic distance between the agent position X and the nearest exit. I'm briefly presenting the discretized problem that I call high fidelity problem in the spirit of model order reduction, little spoiler. And you can find more details about the discretization here in the reference. And the discretized problem is another minimization problem into the approximated feasibility set for the velocities, in which we express the constraint in a slightly different way because we introduce a first order expansion in time of the constraints, and therefore we write it at the time step n, and we can rewrite the constraints in the following way, where d are the positions and the gradient of the position represent the non-overlapping constraints among agents and also among agents and obstacles. How to solve this problem? Well, we rewrote this problem in a saddle point form. So we have a minimization problem that we solved by Usawa algorithm. We look for two sequences of primal and dual solutions. The primal are velocities and the dual are the Lagrange multipliers, which should verify the following scheme, the Usawa scheme, until convergence. We have an initialization of the Lagrange multiplier at the first time step, and then the equation to solve are the primal and the dual problem, where in the dual problem, this is the update of Lagrange multipliers that is made by means of the projection of Lagrange multipliers in the cone of vectors of non-negative components. And this B is the constraint matrix, and rho is just a constant, a user-defined parameter representing the speed of update of the Lagrange multipliers. And once we found velocities and Lagrange multipliers, then the next position is obtained in the following way. Just by updating position by means of the velocities at time n. Okay, so now I'm talking you about the reduced order model. Since this problem is associated with the extreme computational burden in the case of numerous agents. Indeed, you can see here the number of contacts with respect to the number of agents. And this setting is quite even more difficult in the case of predictive studies. It means we have a setting with varying parameters representing, for example, geometric features or material properties. And so we would be obliged to solve this problem many times. For the model reduction, so I'm introducing here the Galerkin projection-based model reduction. We consider some high-fidelity spaces of dimensions nv and n lambda, respectively, for primal and dual solutions. We collect together snapshots of the solutions for several training points representing the geometric parameters, and also time steps that are taken into account exactly as parameters. And what we seek are solution approximations for parameters of interest in a compact set. And this is simply the reduced basis expansion of velocities and Lagrange multipliers in terms of CV and C lambda, which are coefficients, reduced coefficients, which are parameter dependent, and they also depend on the vector of time. So now the point is how to construct the reduced basis. So I'm writing here the construction of the reduced basis, taking the notation for the primal reduced basis, but that's analogous for the dual. We want to construct a reduced basis, and we do that at the offline stage of our parametrized model order reduction technique. And at the online phase, what we do for a new parameter of interest is simply computing the parameter dependent coefficient and then estimate the error with respect to the solution of the full order model. For the primal reduced basis, there are no particular constraints, so I relied on proper orthogonal decomposition on POD. That's a bit more complicated for the dual reduced basis because the Lagrange multipliers represent contact forces. So it's important to preserve the positivity of the contact constraints after reduction. Therefore, the dual reduced basis at curly W plus is this positive span of functions of total dimension R, which has to be much smaller than the total number of contacts to achieve dimensionality reduction. So now the problem is how to find this reduced dual basis satisfying this constraint. In the literature, there is an algorithm. I reported here the reference. This algorithm is able to find the big R basis functions for the dual solutions by solving two optimization problems. A first one is done to compute the reduced coefficients, and you have to solve an optimization problem to minimize the projection error onto the reduced space computed by the R-1 basis functions, and you have also to add the non-negativity of the functions as constraint. And the other optimization problem is the one to find the worst parameter in the greedy search, and this is simply in the greedy spirit of the algorithm. What we proposed here in this work is another greedy base algorithm. The rationale under it is that even in highly congested situations, you end up in having a matrix of Lagrange multipliers that is quite sparse because you don't have all the contacts at all the time step. And so we would like to exploit this fact. Therefore, after an initialization of the geometric parameter, we select this IR that is the largest coordinate of the Lagrange multiplier evaluated at the current geometric parameter mu R. And this largest index is then used to compute the reduced coefficient. So the reduced coefficient at iteration R is nothing else than the IR coordinate of the Lagrange multiplier evaluated at the current geometric parameter mu R. And once we have done that, we have the reduced basis function nu R that is the unit vector of index IR. So with respect to the previous algorithm, we have an explicit expression of the reduced coefficient. And then always, as usual in a greedy-based algorithm, we find the new geometric parameter by maximizing the projection error. So then is the same as in the algorithm before. Okay. I talked to you about the construction of primal and dual reduced basis. Now I'm discussing the quality of the linear approximation and the quantity to assess the accuracy of the linear approximation given by a linear space that I'm calling here hat Vn is given by the Kolmogorov n width. And I'm writing here by using it in terms of velocities, and I'm summarizing here the application of the proper orthogonal decomposition on the velocity snapshots for different training points and a reduced dimension n. And the POD gives us the reduced basis and also the POD eigenvalues. And you can see here on the left the eigenvalue decay with respect to index k of the training points, and on the right the associated energy that represents the associated error computed by neglecting big N minus k points. And so you can see the eigenvalues decay is quite slow, and this motivates further research on nonlinear approaches. So I'm talking you about it later. Here I'm summarizing the reduced order model once we have constructed the reduced basis. And so I had a high fidelity Usawa scheme. Now I propose you the reduced Usawa scheme that is a projection of the high fidelity scheme into the primal and dual reduced basis. We achieve dimensionality reduction when the dimension of the system is given by big N and big R that are much smaller than the total number of high fidelity degrees of freedom. Okay, in the construction of the reduced order model, we should also discuss stability. In the reference that I cited here, in which they proposed the model, the authors were able to guarantee the existence of a constant beta 0, a positive one, such that the high fidelity IMSUP or LBB condition is satisfied for all the training points and all the time steps, where this form B is associated with the matrix of constraint. Then once we introduce the reduced basis approximation, we should compute also the reduced IMSUP constants. And there the problem could also be not well posed. So in principle, there are no guarantees that the reduced couple at V, at W satisfies that constraint, that is the reduced IMSUP constant strictly positive. And so there are several techniques to handle this situation, and I reported them here on the bottom, and they are basically based on enrichment of the primal reduced basis. And I will comment about it in the numerical result. I'm writing here again the reduced order model because it's not as simple as it appears, because unfortunately there are some non-affine terms in the model that prevents the efficiency gain of the reduced order model based on offline and online split. And therefore we are obliged to apply hyperreduction. And in this work, I used a project then approximate approach. That is, I apply hyperreduction and in particular empirical interpolation method after the projection of the high fidelity equation into the reduced space. And I do that for these three non-affine terms in parameters. Okay, I can briefly talk you about the offline phase of EIM, but I think you know. So basically, this algorithm in this offline phase is able to construct a basis such that we can achieve an affine approximation of all the terms in the reduced model. I'm based on a snapshot matrix. This snapshot matrix is generically indicated by S, and inside there could be an independent way the non-affine terms here, and it is an algorithm based on POD, and the reduced basis Q is found by the snapshots, the high fidelity snapshots, and what he imposes is the equality of the snapshots and the EIM approximation at selected points that are the interpolation points, and the total number here is denoted by big M EIM. Okay. I commented about the slow decay of POD eigenvalues, which are empirically related to the Kolmogorov and Weed. And so I'm proposing you here an attempt to mitigate this Kolmogorov barrier to reducibility. To do that, what I'm proposing is a hybrid method combining together a linear and nonlinear approximation. So you have, as before, a linear expansion of primal and dual solutions in terms of reduced basis coefficients that come from the solution of the Galerkin reduced order model. And then we add an extra term, which are a sort of correction given by nonlinear maps. These nonlinear maps takes as input the Galerkin reduced coefficients, the first n and the first r respectively, and they give as output the remaining reduced coefficients. And the rationale under it is that the extra components should be dependent on the first small n or small r ones that carry most of the relevant information. Now the question could be how to find these nonlinear maps. Well, yes, this is an important point in this work. I relied on random forest regression from supervised machine learning. This random forest regression is basically a collection, an ensemble of three predictors that I denote here as phi, that depend on X, that are the input observations that follow a distribution of a random vector big X, and they also depend on theta k, that are some hyperparameters. You can also think of the hyperparameters of neural networks, for example. And and they give us an approximation, a prediction that I call Y, such that the approximation is given by this bar phi, that is a sort of collection of all the prediction, is a sort of mechanism of voting in which the ensemble prediction takes into account the prediction of all the trees from 1 to big K. And so this is why you see that the prediction is actually written as an unweighted average. And the requirement is that the outcome should be quite close to the expected values of this prediction while giving as input the observed data. Okay, the construction of a random forest relies on two phases that are usually called bootstrapped phase and aggregation phase. This is why maybe in the literature you encountered the name bagging, because it's an ensemble of the two. It's basically given by a dataset decomposition into randomly chosen training subsets that I called decay, and then there is the aggregation phase to provide the ensemble prediction. The rationale under this technique is that we would like the random forest variance to be very small, and this variance, because we want to do predictions, this variance scale with this quantity where rho is the pairwise correlation among trees, and sigma is the variance of each tree. So what random forest wants to do is lowering rho by not increasing too much the variance sigma. Okay, so I applied this technique, and now I'm showing you some numerical results for my setting. In my setting, I have 20 agents that are placed in a region of size small l all times big L all, and they want to exit. And that's a parametric setting in which two varying parameters are considered. We have the exit width, where L exit is this parameter here, and we have the spontaneous velocities of all the agents. And we assess the accuracy of the reduced order model by this average error based on the L2 norm. Okay, here I'm presenting you the construction of the dual reduced basis. So on the left, I'm comparing together the greedy index selection algorithm with the orange one that is the existing algorithm in the literature. And I'm computing the maximum projection error with respect to the iterations of the algorithm, and the total number of iterations then gives the total number of the dual, the total dimension of the dual basis. And as you can see, the greedy index selection algorithm is associated with a much lower error for a smaller number of iterations, while for small number of iterations the behavior is quite comparable, is quite equivalent. And the existing algorithm in the literature requires much a greater number of iterations to achieve a good accuracy. And on the right, I depicted some out-of-sample errors of the reduced basis with or without the hyperreduction. And I did that for several dimensions of the primal and dual reduced spaces. as you can see, to achieve a very good accuracy, you need quite a complete basis, in particular for the dual basis. You need all the modes of the basis, and this is also representing the difficulty of the problem to be approximated by a linear method. Here I'm showing some results on the stability of the reduced order model, but basically I computed the high fidelity and the reduced IMSUP constants for different values of out-of-sample validation parameters, and I observed that there is not a degradation of the reduced constant with respect to the high fidelity one, and also for a smaller number of primal and dual reduced basis dimension, you basically have smaller values but the same order of magnitudes. So I'm a bit lucky in this application, and I don't need a further work on basis enrichment. Okay, now the most important result, I think, is in this slide. I'm applying the nonlinear reduced basis method. So I'm relying on the combination of linear plus nonlinear reconstruction given by machine learning. And this is the performance in orange in terms of the out-of-sample relative error for both velocities and Lagrange multipliers. And this is depicted in orange with the mean that is depicted here. And for all the validation parameters, and I'm comparing the nonlinear reduced basis method with the linear approximation. So for the velocities, the POD, and for the Lagrange multipliers, the greedy index selection algorithm. And then I'm also comparing these two techniques with the regression of the solution that here I'm dubbing regr. This means that I'm simply using the random forest regression to approximate the solution without taking into account the reduced order model and the Galerkin coefficients. Okay, so here I'm depicting the out-of-sample errors, and you can see that the gain in accuracy with respect to a linear approximation is more or less 1 order of magnitude with respect to POD and greedy index selection, and this is even more than 2 orders of magnitudes with respect to the simple regression of solutions. So there is an accuracy gain effectively. And in this table, I wanted to focus on the wall clock time and the speed up factor, because with the reduced order model and with the nonlinear reduced basis approximation, we were able to obtain a speed up factor that is always bigger than 7 for this very small application of 20 agents, and we envision it to be even larger for larger values of particles. Okay, and the online cost of adding the machine learning correction is quite negligible, and so the reduced order model and the nonlinear reduced basis technique have more or less the same online cost, while the second one achieves a very better accuracy. Here I simply wanted to depict particle positions for a smaller number of modes of the primal variables for a generic out of sample configuration in Xi-valid, that is the validation set of parameters. And okay, so summarizing what I talked to you about, you can look at this work as an attempt to mitigate the Kolmogorov barrier to reducibility. So the simple reduced basis technique seemed to be not enough, and I combined that with a nonlinear approximation. In particular, for this application, I combined it with random forest regression for the reconstruction of reduced coefficients coming from the solution of the Galerkin reduced order model. And what I did was done in a simple application of 20 agents. The idea now is to consider more complicated simulations with a very, very high number of agents and basically the same model. So I'm envisioning to do that by using the Scopy++ code that is a code developed in Ecole Polytechnique to deal with these highly congested situations. And yeah, so here I'm considering the main references. You have the first one, that is the proposed model. The second one is the paper in preparation, almost in submission, so stay tuned if you are interested. And the third and the fourth are the works on nonlinear approximations as the one that I'm using. So there are two, these are the two papers that inspired my work, and they are based on approximation of hyperbolic equations. And so, yeah, that's it. Thank you for the attention, and don't hesitate to write me if you have similar models or similar methods. So, yeah, thank you.
Thank you, Giulia, for your talk. Now is question time. So if you have a question online, you can simply unmute yourself. Yes, Ivan, you can ask.
Hi, Giulia.
Hi.
Very nice talk. Thank you very much. Actually, I have a couple of questions.
Yeah.
I don't know. Can you hear me well?
Yeah, I quite can hear you.
Okay. When you introduce the Java algorithm at slide 5, you use the parameter raw. Can you comment on how you choose it and how your convergence depend on the value of the parameter?
Yeah, actually, I didn't talk about it, but in the theory of this algorithm, that is a range of convergence in terms of raw, and this range of convergence is application dependent. So it depends on your problem. For my problem, I had a certain range of the type 0 row bar, where row bar is a positive maximum raw that I could pick up, and this raw in my application was really strictly dependent on this constraint matrix B. And if you if you pick your raw inside the range, you have a convergence of the scheme. So it is quite a common result in theory, but you have to pay attention that is application dependent. So you have to write the maximum in terms of the unknowns of your problem.
Okay, so
and what I did was simply taking the value at the average of this interval to make sure it was fine.
Okay, so basically, if I understood correctly, you like in order to say that the scheme is stable, you need to choose raw such that the scheme is somehow contractive. Yeah, like if
Yeah,
it is
yeah. These are two
okay.
different things. One is the stability of the scheme, and one is this property of convergence of the
Yeah.
Usawa. Yeah, I would say that the stability is more related to the problem itself, but this raw is really dependent on the algorithm you choose to solve it.
Okay, thanks. Then I have another question, if you don't mind.
Yeah, don't worry.
So you introduced the greedy algorithm, okay, before, and then you stated your own algorithm, which is based on greedy index selection. Do you have some comparison on the convergence? Is your algorithm faster in some way than the standard greedy?
Yeah, I made a simple comparison based on the computational cost, and I found this algorithm that I propose more or less 8 times faster than this algorithm here, because this algorithm, that is the existent one in the literature, is based on this minimization problem that is quite hard and costly, because you have to minimize this problem with this constraint of non-negativity of the function. What I did in Python was relying on the convex optimization package for quadratic programming, and yeah, it is quite a hard problem to solve, so it's a bit costly. And rather than this, in the algorithm I'm proposing here, the computational cost is much less, because you have an explicit expression of the reduced coefficients. So you have nothing to solve here. You basically take the IR coordinate of the Lagrange multiplier, and that's it.
Okay, nice. Then I have a question about the enrichments of this further point problem, because you said that you didn't need them for the numerical results, which is quite surprising, I'd say. But what are the techniques that are basically used for the enrichment in the case where you actually need them? Can you comment on
Okay.
that?
Okay, that's not my case, but I read something about it. You should find it in a paper from Idrissa Niak at the Virginia Larcher, and there are some techniques that are based on error estimations, for which you pick up a dimension of the primal basis that can be also very small, and then you iteratively add some modes. These modes are added in such a way that at each iteration of this procedure, the projection error is smaller than a user-defined threshold. But to my best knowledge, I think it relies on error estimation, and so I did not done that to my project. It was not strictly needed, and it's
Okay.
one of the perspectives.
Okay, thank you. And if you please go to slide 23.
Yeah. Yeah.
I couldn't have. Okay, so I noticed that on the figure B, the POD, okay, it's the base, like the average error kind of goes down with the number of phases 50. Like, can you explain why this goes down? Like, don't you compute more, or you just, or like at the figure B, like the blue line, you have your error with respect to 3D index selection. When you reach R equal 50, your error kind of goes down.
Yeah.
Why does it happen?
Okay, this is happened because it is related to the GIS algorithm, because this algorithm, once it achieves the total dimension of the dual reduced basis, it gives error 0, projection error 0. So
Okay.
it's not astonishing that when you have like then it should be 58. The picture, it can be a bit strange, but when you have like 58 modes, you go down to 0 because it means that in the greedy algorithm you found a sort of repetition of coefficients.
Okay.
And at that iteration 58, then you have a really 0 projection error.
Okay, thanks. I had the last question, but you actually answered this at the end of the talk. I mean, if there is some link between microscopic and macroscopic model, and you said that you haven't still worked on the media agent parts, so okay, I think it's not time to ask the question yet.
Yeah.
Thank you for everything. It was a very nice talk. Thank you.
Thank you.
Okay, are there other questions from the audience?
Maybe I have one. Giulia, can you hear me well?
Yes.
On this slide, I see that there is a large confidence interval in the nonlinear reduced basis, but is it because of the regression on the coefficients, or do you know why this happened?
Yeah, I think that this is due to the prediction made, the correction made by the machine learning part, so the correction made by the random forest. And I also considered, I also did a test that was considering a different number of training points, and I saw that the behavior is quite the same also in that case. For all the validation parameters. So I observed this, that the dependence on the training point is much stronger in the case of this nonlinear reduced basis reconstruction rather than the linear approximation. So it made me, it suggested me that this nonlinear reduced basis approximation is a bit more is associated with the larger variance in general.
Okay.
Okay, other questions online? Okay, if not, we thank our speaker again.
Thank you.
Thank you, Giulia, for your talk, and see you next week for another AJS. Thank you, everybody.
Thank you.
Grazie, Giulia. Ciao.